In this video, you will continue the engineering applications of integral to the second application, which is the area of a surface of revolution. So previously, we have talked about how to use integration to get a formula and function of the arc length. And in this video, you will use integration to calculate the area of a surface of revolution. But first of all, what is a surface of revolution? So if you look at your notes, a surface of revolution is formed when a curve is rotated about a line. Okay, so let's say you have a curve and y and x axis. So let's say you have this curve. If you rotate this curve about the x-axis, right? If you rotate this curve, then it will form some surface. Okay, this is the surface of revolution, and we're going to find out. We're going to derive a formula how to calculate the area of a surface revolution. So we need to define the area of a surface of revolution such that it corresponds to our intuition, such that it is natural for us to be thinking that's the logic of getting to the final formula. Just like what we did previously with the arc length. So previously in the arc length, when you have any curve, so what you did is that we dissect this curve into several segmented lines, straight lines, and then we estimate or approximate the length of the curve by approximating the length of the segments and sum it up all together. Thus we use the integration to sum it up from the limit a to b. So we want to do something like that this time for the surface of revolution. Let's start with some simple surface. Okay, let's say you have a cylinder, circular cylinder. Okay, so this is your cylinder. So you have this cylinder with the height h and the radius r. Okay, so you know that the surface area of a circular cylinder with radius r and height h, the area is taken to be 2 pi r h. Okay, because we can imagine cutting the cylinder and unrolling it. Okay, if you just cut open the cylinder, you will get this rectangular form, and the dimension of this rectangle will then be, this is your h, and the length here is 2 pi r, which is the circumference of the cylinder, of the circle here, right? Okay, so then the area simply is the height times the width, which is 2 pi r times h. So similarly, we can take a circular cone with base radius r. Let's draw that. So you have a cone here. The base, it is a circular cone. So you have this base radius r. Okay, and the slant height is L. Then maybe you can cut it out along the dashed line here and flatten it to form a sector of a circle. Okay, so it will become something like this. Okay, where this is the angle and this is your slant height L, and the circumference of this sector is thus equal to 2 pi r. So the angle of this given circle, sector of a circle, is equal to 2 pi r over L. In general, the area of a sector of a circle with the radius L and the angle theta, the area equal to 1 over 2 L squared theta, and theta is equal to 2 pi r L. So you can substitute this, area equals to L squared times 2 pi r over L, and simplify this to get area equals to pi r times L. Therefore, we define the lateral surface area of a cone to be A equals to pi r L. This is okay because we have a simple surface. We just have the circular cone. But what if we are given a more complicated surface of revolution? Okay, so we can follow the same strategy that we used with arc length, where we approximate the original curve by a polygon. So in this case, let's say let's say you are given a more complicated surface, okay, a curve. When you rotate about the x-axis, okay, so you will have a more complicated surface. So what you want to do is to follow the same approach like we did in the arc length, where we dissect this area into several segments such that we can find the area of more simple surface. So by approximating the surface, then we can sum it up all the surface area to get the actual surface area of a revolution of the whole curve here. Let's do that to get the derivation. So let's say we are given a curve, okay, when it's being revolved around the x-axis, so we get something like that maybe. Okay, so we want to find the surface area of a revolution of this surface of this shape. So what we're going to do the same approach like we mentioned previously. Okay, so what we're going to do is we dissect this into several shapes, several pieces. Okay, then we're going to find each of these area and we're going to sum it up. So this surface area, to find the surface area, each of these bands, so these unlike the segments of line in the curve arc length just previously, in this case we call these segments as bands. So each of these bands, the area can be considered as a portion of a circular cone. So imagine if you have a circular cone, just like what we did previously. So this is your circular cone, and let's cut it up into two parts. Okay, so you have this cone where the bigger cone, you can have the length as L1 and the length of the lower cone as L, and then the radius of the small cone is R1 and the bigger cone is R2. But you just want the area of this band here, the segmented circular cone here, and you don't want the top of the cone. So that one, okay, so that when we put a dash, we want to remove the upper cone and just want to find out the area of the shaded area there. So what we can do is to get the area equals to area of the bigger cone minus the area of the smaller cone that we want to remove. So area of the bigger cone is pi R2 L plus L1 minus the area of a smaller cone is pi R1 L1. Okay, then we can expand and simplify this expression to pi to L. So A equals to pi times R2 minus R1 L plus R2 L. Okay, this should be L1. But we don't want the term L1 because we are only interested in the highlighted segment where we want the R1, R2 and L. We don't want to have the L1 in this expression, so we want to get rid of it. So we use the concept of a similar triangle. You can draw the similar triangle. Oops. Okay, so this would be your theta, and then this is a right angle, so this is R1, R2, and here is your L1 and here is your L. So the ratio between L1 and R1 would be the same with the ratio between L1 plus L over R2. Then you can just rearrange this so that you want to eventually eliminate L1. Okay. So L1 equals to R1L over R2 minus R1. I don't need to actually go to that detail because well, I just need to replace this term into this formula. So let's do that. So this one equals to this one. So A equals to pi times R1L plus R2L. That will be equal to pi times R1 plus R2 times L. And then let's make our life even more easier. We don't want this R1, R2. Let's define just R equal to R1 plus R2 over 2, the average radius of this whole segmented circular cone. So R equals to R1 plus R2, the average radius of the band. So R1 plus R2 will be equal to 2R. And this one we substitute into the area. So we get area equals to pi times 2R times L equal to 2 pi RL. So that will be the area of one single band in this segmented, where is it? Yellow, okay. Yeah, that will be the area of the segmented band, each of these, okay. So we have the R, this one. Okay, here, if you want to just illustrate, this would be your R, R2 and R1, okay, and then this would be your L, something like that. So at least we get something to a starting point to derive the formula to get the surface of revolution in terms of x and y after this. Okay, let's get to the real work where we want to write the area in terms of x and y instead of just now we have A equals to 2 pi RL for a given band, which is part of a cut circular cone. So if, let's say in this diagram here, we are given the function y equals to fx, then we rotate this function about the x-axis, and we will end up with the blue shaded region, which is the surface of revolution, and we want to find out the area of this surface of revolution. So in this curve, the interval of x is from x equals to a to x equals to b. So we divide this interval into n subintervals with the endpoint x naught. So a here is the beginning of the interval x naught. Then we have this point p naught, and until b. So b is the end, the final point. When so the point here is pn. Okay. Okay, so we have divided this interval a to b into n subintervals where the x delta x is the constant, but delta y is not. So from a equals to 2 pi RL, so we can for each band here. So look at the second diagram here for pi minus 1 to pi. So you can get the y. So you can get this radius here is the length is yi minus 1, and here the length is yi. Okay, so then the r is what? R is R1 plus R2 over 2. So R equals to yi minus 1 plus yi divided by 2. And then what is L? L is basically the slanted height here, okay? So basically L is pi minus 1 pi. So this is the length of the slanted height. So substitute this R and L into the area. So you have A equals to 2 pi times yi minus 1 plus yi over 2 times the L. L is pi minus 1 and pi. This is just the length. So previously in the arc length function, we've had pi minus 1 pi equal to the square root of 1 plus f prime of xi star, everything here squared, delta x. So we can substitute this into the area formula. But before that, because if we divide the interval AB into a very large number of segments n, then the interval becomes very small, i.e. the delta x is so small such that yi can be approximated to be, yi is actually just f of xi and can be approximated to be equal to f of xi star, because as I mentioned earlier, in a small section you can approximate it to, this is the xi star. So because the segment is very, very small, you can approximate it to be equal like this. And yi minus 1 also equal to f of xi minus 1 and can be approximated to be equal of f of xi star. Okay, so we're going to put this into the formula here, and this also into this formula here. So we have a equals to 2 pi times, so yi minus 1 is fxi plus yi is also fxi, so we put there 2 fxi star divided by 2 times the square root everything there, 1 plus f prime of xi star squared delta x. Okay, so simplify where you can. So you will have area of a segment equals to 2 pi f xi star times the square root of 1 plus f prime xi star square delta x. So this is the area of one band. So well, you can guess the next step is to sum up all the area of each band. So you can take the limit as n approaches infinity and sum it up from I equals to 1 until I equals to n, 2 pi f xi star square root of 1 plus f prime xi star everything squared and delta x. And as you know, whenever you have the formula with the limit expression, is not very useful, so you want to put this in terms of integral. So you have area equals to integral from a to b 2 pi f of x times the square root of 1 plus f prime of x squared dx. Also, this function can be also written as in terms of the Leibniz notation, where this one is just put it as fx, and the inside you can put in terms of dy dx. Sometimes it's more helpful that way to help you familiarize, but it's actually the same. And you can also write down this notation using the arc length function. The arc length function function. Yeah. So previously you have this arc length function as the integral of 2 pi y ds, where ds is the 1 plus dy dx squared dx. Okay, so this is if you have the function rotated, if you have the curve rotated about the y-axis. You can also manipulate the this function, this formula, into something when you have a surface of revolution rotated about the y-axis instead. Okay, for example, you can look at this in your notes and also in this PDF slides that I have given you. So let's say if you have a function that is rotated about the y-axis, then you have a different limits here. So let's just do that briefly. So instead of a and b, so let's say if your surface of revolution is rotated about the y-axis from y equals to c until y equals to d, then your limit would just be c to d, and then instead of fx you will have g of in terms of y, and of course inside here you will have the g prime of y, everything squared, and also dy. Okay, same thing here. So from C to D, here is your gy, g in terms of y, And here you will have dx over dy with respect to y. And you can also manipulate this in terms of x, and dx is dx dy and dy. Okay, just look at the curve where it is rotated about which axis, and then you can either choose this notation or this notation to find out the area of a surface of revolution. Okay, let's do an example to find the surface of revolution, the area of a surface of revolution. So example 3, the curve y equals to square root of 4 minus x squared with the interval x between -1 and 1 is an arc of the circle x squared plus y squared equals to 4. Find the area of the surface obtained by rotating this arc about the x-axis. The surface is a portion of a sphere of radius 2. So, well, you know this is equation for a circle. So whenever you are given x squared plus y squared equals to 4, meaning the radius is 2, but then our limit is just 1. So the radius in this case is 1 to -1 to 1. So you are asked to find the area. So follow the steps. So first, find the dy dx. You're given y, so you can find dy dx, and use the formula of surface of revolution. Substitute it into here and put the specified limits a and b. So a is -1 and b is 1, and solve it. Okay, for this question, y equals to 4 minus x squared square root. So you can get dy dx equal to 1 over 2 times 4 minus x squared -1 over 2, and also differentiate the terms inside, get -2x, and you can eliminate number 2. So dy dx equal to -x over square root of 4 minus x squared, and you can square this term dy dx squared equals to the whole thing squared, so you get dy dx squared equal to x squared over 4 minus x squared, and that's your formula is s equal to -1 and 1, the limit is -1 and 1, to pi f of x 1 plus dy dx squared dx. Alright, so you substitute this into the formula, -1 and 1, 2 pi, so fx is 4 minus x squared, and the square root of 1 plus x squared over 4 minus x squared dx. Then yeah, just continue, 2 pi squared, and this whole thing here you may want to simplify a bit. So this one gone. Okay. So this one gone, and this is just 2. So at the end of the day, just integrate 4 pi with respect to x. So you get 4 pi x, put in the limit -1 and 1, and you get 8 pi. So this is your area.